Chapter 11 was where we really started to shift our focus on learning a lot of new content and apply a lot of the content that we have learned throughout the year to really specific scenarios. Um, so chapter 11 is where we started that, and we started that with solutions. This was really looking back and applying a lot of what we did in matter and bonding and reactions and moles and stoichiometry and gases, and it sort of culminated in understanding really what a solution is and how they behave. We started off our discussion with looking at solubility. We defined solubility as the amount of solute that can dissolve in a certain amount of solvent at a specific temperature and pressure. When we report solubility, we have to talk about what the solute is, in how much solvent it will dissolve, and at what temperature and pressure, because all of those factors can change how much of a substance will dissolve. And that's what solubility is. So it's really specific when we communicate that information. The solute is what is dissolved. The solvent is what does the dissolving. Together, they are considered a solution, generally because we can have solute and solvent in any phase of matter, although we focused on mostly solid and gaseous and liquid solutes in just a liquid solvent. Either of those two can be at any phase. If we have to question what is the solute or what is the solvent, it's generally the solute is generally what's in a smaller amount, and the solvent is generally what's in a larger amount. If you're making the solution in the lab, you will be able to determine what is dissolving in what, so that should help you answer the question. But if we ever have, let's say, a solution of gases, well, which gas is dissolving in the other? Or if I have two liquids, which liquid is dissolving in another? If they just both are mixing together, we usually use the amount to sort of, in those odd cases, sort of define what the solute and solvent is. The term soluble means it will dissolve. Insoluble means it will not. Miscible means the two things will mix. Immiscible means they will not. Now, in terms of how can I predict if a solution will form, first of all, remember that solutions are homogeneous mixtures. Things like colloids and suspensions are heterogeneous. So they're mixtures, they have variable compositions, but heterogeneous means that the components of the mixture are not uniformly distributed. A solution, by definition, has components that are uniformly distributed throughout, so that's what makes them homogeneous. How do we predict if a solution will form? Generally, we use like dissolves like, and that goes back to molecular polarity, intermolecular forces, all of that stuff. Nonpolar solutes will dissolve in nonpolar solvents. Polar solutes will dissolve in polar solvents. We said it has to do with the similar intermolecular forces. We looked at the overall solution-making process, that we have attractions of the solute being broken, we have attractions of the solvent being broken, energy spent in both of those processes, and then the solute and solvent come together to form new attractions, and we get some energy back. Really, the solution's only going to form if, at a bare minimum, the new attractions are somewhat similar to, hopefully stronger, but somewhat similar to the attractions that existed before with the isolated solute and solvent. For ionic substances, we throw that under the polar solute category because ionic substances have ions, positive and negative ions. So they will act polar in a solution, but with ionic substances, we have to go one step further, because if they're going to dissolve, they really can only dissolve in polar solvents, but then we have to check if the polar solvent, like water, can overcome the lattice energy that's holding the ions together in the solid ionic compound. And we have solubility rules to help us determine if the water will be able to pull apart those ions from each other. So that goes back to solubility rules. We looked at factors that affect the rate of dissolving, meaning how fast something will dissolve, not how much, how fast. Agitation or stirring, right? Increased agitation or increased stirring will increase the rate because we are providing some additional kinetic energy to help the solute and solvent particles come into contact with each other. Temperature, increasing temperature will also increase the rate of dissolving or dissolution. because again, we're providing more kinetic energy to help the solute and solvent meet and connect and make those new attractions. And then surface area, if we increase the surface area, meaning increase the number of exposed faces. So imagine taking like a sugar cube and crushing it. So now I have a granulated sugar, right? Granules instead of just a solid cube. Now I have exposed more solute particles to collide with solvent, and that increases the rate of dissolution as well. Now a note here, all of these really only work for really solid solutes. Temperature, definitely not for gases. It's hard to talk about the rate of liquids dissolving in each other. You know, agitation could help the two liquids mix together, but because they're the same phase, it's odd to talk about the rate of a liquid dissolving in another liquid. So really these are the rate of a solid solute dissolving in a liquid. Surface area really only correlates to a solid, right? If you think about it, you can't increase or decrease the surface area of a liquid or a gas. So those are only really for solid solutes. Now, we also went over factors that affect solubility. This is how much will dissolve. For solids, increasing the temperature, right, will increase the solubility. But for gases, decreasing the temperature will increase the solubility. And we related it back to gas laws and the overall behavior of a gas. If you throw a solid in some water, just based on density, it's going to sink to the bottom and stay there in the liquid. But a gas, we know that their densities are way less than liquids and solids, and they expand to occupy their container. So we can't just take some gas and just throw it into a solvent. The gas needs to be kept, really forced to stay in the liquid, in the solution. And how do we do that? Well, as long as the particles are close together, we can force it to stay in a contained given area. Decreasing the temperature based on what we know about how gas particles behave will bring them closer together. Pressure, there is no effect on solid solubility, but there is an effect on gaseous solubility for the reasons that I just explained. Increasing the pressure will help keep more gas forced in the solution, keep the particles closer together. So those are the relationships we should know there. We looked at solubility curves. Solubility curves basically plot how much of a substance can dissolve, what maximum amount of a substance can dissolve in a specific amount of solute at a given temperature. And here's an example of some solubility curves for some different substances. The chart that we looked at in class had both solid and gaseous solutes, and if we have to add, these are obviously all solids based on their lines, but if we had to add something that represented a gas, it would look something like this, because gas solubility decreases with an increase in temperature, so their slopes are going to be negative, where the solid solute slopes are going to be positive. We have to remember that solubility is based on a specific amount of solvent, as are the solubility curves, as are these graphs. This one is based on how much of the solute can dissolve in 100 grams of water. So for example, and we'll write it up above, let's look at potassium chloride, KCl. At 60 degrees, we can dissolve about 45 grams of potassium chloride in 100 grams of water, because that's what the graph is telling me, at 60 degrees Celsius. If I wanted to determine how much KCl could dissolve in any other amount of water, I just set up a proportion, right? If it's 45 grams in 100 grams of water, then in 200 grams it would be twice the amount. It would be 90 grams. So those calculations are simple as long as you understand what you're reading from the graph is per 100 grams of water. And the other thing that we can relate to these graphs are the terms unsaturated, saturated, and supersaturated. So if we're describing the solution as unsaturated, we're saying that there's less than the maximum amount of solute dissolved, which means the solution can hold more solute. That means I'm going to be somewhere underneath the solubility curve, underneath the line. The seed crystal test, remember to test for, we wouldn't be able to necessarily look at the solution and say, oh, it's unsaturated, but if we try and add even one more crystal and that crystal dissolves, then we can conclude that the solution before was unsaturated. A saturated solution is when we have something directly on the line, like the KCl example we just read before. What we were reading is at 60 degrees Celsius in 100 grams of water, we can dissolve a maximum of 45 grams of KCl. No more will dissolve. So if we go to add a seed crystal, we're going to see that crystal just fall to the bottom. Then supersaturated, special condition. These solutions have more than the maximum amount dissolved. These would be above the curve. Seed crystal will cause precipitation or crystallization because these solutions are super unstable. That extra solute that's dissolved does not really want to be there. We can only create a supersaturated solution by heating up the solvent to dissolve more and then slowly cooling it down, and hopefully some extra stays in there. They're unstable, and not all salts, not all solids or gases for that matter, are good at creating supersaturated solutions, but sodium acetate is a really good example of a salt where you can easily create a supersaturated solution, and that's the example that we used in lab. We then looked at solution concentration. So when we talk about saturation level, saturated, unsaturated, supersaturated, we're talking about how much solute has been dissolved relative to the maximum. When we talk about concentration, we're talking about how much solute has been dissolved compared to the solvent, right? So saturation and concentration are two completely separate things. Concentration is really just looking at that ratio of solute to solvent. And generally, if I have more solute than solvent, the solution is relatively concentrated. If I have more solvent than solute, it's relatively dilute. And there's a couple of ways in which we look at to express concentration. Every method of expressing concentration would be used in a specific scenario. Percent by mass or volume would be used if we commonly measure the solute and solvent in either a mass unit or a volume unit. We looked at molarity, which is specifically moles of solute per liters of solution. We looked at molality when we looked at colligative properties, which is moles of solute per kilograms of just solvent. And specifically molality is used because that's not affected by temperature. Because I don't have a volume unit there, volume is not affected, or volume is affected by temperature. Volume will expand and contract, but mass, conservation of mass, is not. We looked at parts per million, which is essentially the same setup as percent by mass, but we use parts per million if I have an extremely dilute solution. So really extremely small amounts of solute and solvent. In class we talked about how it's used to measure dissolved substances in large amounts of water or pollutants in the air. And then the last formula we looked at was the dilution formula. M1V1 is equal to M2V2, which is going to help us calculate if we want to create a solution from a stock solution, what volume of that solution would we need? Or if I have a solution and I add more solvent, what will the new molarity be? The idea here is that the moles before we change the amount of solute, or the solvent, are equal to the moles after. That's staying constant, but the concentration will change because concentration is how many moles of particles of solute we have in the given amount of volume there. We looked at the appropriate ways to make solutions. We will have to, if I want to make a specific volume of concentration, we have to do some math to figure out what amount of solute we need. We mass it out. We add it to the appropriate volumetric flask. We add a little bit of water, make sure that the solute dissolves, and then we add the rest of the water up until the graduation line of the volumetric flask. Remember, these are really precise. It's a really precise piece of glassware that only has one single graduation on it for a specific volume. So if you're making a 500 milliliter solution, you're going to grab a 500 milliliter volumetric flask. If it's 100 milliliters, you're going to grab a 100 milliliter volumetric flask. There's only one graduation on the specific piece of glassware. If we want to dilute a solution, so we have a stock solution in the lab that's at a particularly high concentration, then we can use the dilution formula to say, okay, I'm going to take a small amount of this concentrated stock solution, put it into a new volumetric flask, and then add water to it, so now I have a more dilute solution. The same rules apply. You need a specific volumetric flask for however much solution you want to make, and then you're adding water to the graduation mark. The last thing we talked about and looked at was colligative properties. So colligative properties, remember, are properties of a solution that depend on not what the solute is, but how much of the solute is dissolved. It's only looking at how many particles are dissolved. And we focused on two colligative properties: boiling point elevation, the idea that as boiling point, or as the number of dissolved particles increase in a solution, the boiling point is going to increase as well. And freezing point depression. As the concentration of particles in a solution increases, the freezing point is going to drop. And we looked at two formulas that can help us calculate how the temperature is going to change. And really the structure of them is similar, just one is calculating by how much the boiling point is going to change, and one is calculating by how much the freezing point is going to change. The three components of this calculation is the concentration of the solution in molality. So it's moles of solute per kilograms of solvent, so that it's not affected by the temperature change. K, which is a boiling point or freezing point constant. This is specific to the solvent, and I gave you a table here. So for example, water has a boiling point elevation constant of 0.52 degrees Celsius per molal. What this means is that for each molal of particles, the boiling point is going to increase by 0.52 degrees Celsius. But for something like benzene, its boiling point elevation constant is much higher, 2.53 degrees Celsius per molal, which means that we can change, with the same concentration of particles, we can change benzene's boiling point more than water, or it will change more than water. For each molal of particles for benzene, its boiling point is going to increase by 2.53 degrees Celsius. And the same rules apply for freezing point depression constant, except the temperature is dropping below the freezing point. The most important thing here in this calculation is I, which is known as the Van't Hoff factor. That name's not super important. What is important is that it's representing the number of particles that the substance dissociates into. So what's important here again is not necessarily the concentration of the solution, but the concentration of particles, and that's what we're going to go over here. For us, ionic substances and acids, which we don't have to worry about here because that's a separate chapter, will split up or dissociate in water. Molecular covalent substances will not. So here, glucose, the I value would be 1 for glucose, because when it splits up, it just stays as one individual particle, right? It's just sugar molecules breaking apart from each other. But when something like magnesium fluoride dissolves in water, that magnesium fluoride, MgF2, that ratio is not going to stay together as one unit. It's going to split up into 3 separate ions, 1 magnesium plus 2, and 2 F minus 2 ions. So that's 3 total ions that we're going to get. So what this number is saying is, let's say I had a 1 molar solution of glucose. Well, I'm going to have a 1 molar solution of glucose molecules. But if I have a 1 molar solution of magnesium fluoride, I'm actually, once it's dissolved, going to have 3 molar of ions. Because for each MgF2 unit, I'm going to get 3 separate ions. So the ion concentration is actually going to be greater than what the solution concentration is for the unit. NaCl will have an I value of 2. Aluminum nitrate will have an I value of 4. Calcium phosphate, will have an I value of 5. And chloromethane, being molecular covalent, like glucose, will have an I value of 1. So assuming equal concentrations of all of these solutions, doesn't matter if I have glucose or chloromethane, their solutions are going to have the same properties in terms of freezing point depression and boiling point elevation if their concentrations are the same. But if I had an equal concentration of all of these ionic solutions, let's say 1 molar of each, this one's going to affect the boiling point and freezing point the most, because I will have 5 molar of ions and then 4 molar of aluminum nitrate, 2 molar of NaCl, 3 molar of MgF2. But the calcium phosphate, because I will have the most dissolved ions in that solution, again, assuming all the concentrations of these guys are equal, will have the most effect. And we worked on some calculations, plugging in, so you should be able to perform those. The only other thing that I want to mention, again, wasn't something super new, but applying the idea of solution concentration to stoichiometry, we looked at what we called solution stoichiometry. Molarity is a conversion factor, because molarity is relating the number of moles of solute to liters of solution. And it's just yet another way for us to get the number of moles of a substance. So if I have the volume of a specific solution, let's say 0.5 liters, and they tell me that it's a 2 molar solution, well, that's enough information for me to figure out how many moles of the substance I have. 2 molar, which means I have 2 moles per liter. I have half a liter of it, 2 times 0.5, that means I have 1 mole of this substance. We'll call it substance A. And then once I have moles, we know what to do from there. We can use the mole ratio from the reaction. We can calculate how many grams of A are in that solution. But again, just reinforcing the idea that molarity is a conversion factor that we should be able to know how to use in a stoichiometry conversion or in any mole conversion. So that brings us to the end of chapter 11, and you should be ready for your chapter 11 throwback quiz.